Hello, everyone, and welcome. Today, we're diving deep into a true technical masterclass explainer on prestressed concrete. If you're in structural engineering or studying to be, you already know that mastering this material literally changes the game. Now, we aren't going to sit here and read a boring textbook, okay? We're going straight to the industry's top technical manuals to understand exactly how and why we build modern infrastructure the way we do. So let's jump right in. To understand the solution, we've got to look at the problem first, right? As Chapter 5 of the LRFD manual points out, conventional concrete is fantastic at resisting compression, but it has a massive Achilles heel, tension. It practically fails and cracks when it hits just 10% of its capacity. Think about it. You apply a load, the bottom of the beam stretches, and boom, you get cracks. In bridge design, this is a huge headache because it drastically limits the span lengths we can safely and efficiently build. Here is our roadmap for today. We'll cover the principles of pre-stressing, structural advantages, key infrastructure elements, applications in bridges, and we'll wrap up with some real-world case studies.
Let's kick things off with Section 1, the principles of pre-stressing.
You know, to really grasp pre-stressing, I love this classic analogy from Gustav Magnell found in the PCI Bridge Design Manual. Imagine grabbing a row of a dozen loose books and trying to lift them all at once into the air. If you just support them from the bottom, the middle ones are definitely going to fall out. But if you squeeze them together really hard from the ends, you create internal compression. Suddenly, those loose books act like one solid beam. They can support themselves and even extra weight. Well, that is exactly what pre-stressing is. It's the intentional introduction of a permanent internal compressive force before any real service loads are applied. So, how do we pull off that book magic in real life? LRFD's Section 5.3 breaks it down perfectly. We use incredibly high-strength steel tendons or strands and tension them right through the concrete. As you visualize placing these steel cables at the bottom of the beam, right where tension happens, and pulling them, we are pre-compressing that exact zone. That way, when heavy trucks drive over and try to bend the beam, that external tension first has to fight against our built-in compression before the concrete even thinks about cracking. It's pure genius. Moving on to Section 2, let's look at the structural advantages of doing all this. Drawing from Chapter 8 of the PCI manual, let's put them head-to-head. With traditional reinforced concrete, we basically assume the section is going to crack under everyday traffic loads, which traps us into designing short spans with really massive pieces. But with prestressed concrete, the story changes entirely. We keep the entire cross-section completely crack-free. By utilizing 100% of the material, stiffness shoots way up. What does that mean for us? We can design much thinner elements, shed dead weight, and easily reach spans over 60 meters, all while keeping the internal steel safely protected from corrosion. It's an absolute win-win. And hey, if you're a numbers person like me, this load deflection chart from the PCI manual is the ultimate mathematical proof. Look at the bottom curve. That's your traditional reinforced beam. See how quickly it deforms and cracks once it hits the service load? Now look at the top curve, the pre-stressed concrete. It stays linear and highly rigid for so much longer. The big takeaway here is that pre-stressing massively reduces deflections under everyday loads. It's a huge performance upgrade. Of course, to handle these crazy internal forces, we can't just use whatever concrete mix is on sale. Check out Table 7.1 from the Design of Highway Bridges Manual. Standard stuff uses classes A, B, or C. But the second we enter the pre-stressing world, we jump to Class P, which demands strengths over 4,000 psi, or 28 megapascals. And for the really extreme designs, we go to HPC, high-performance concrete, easily topping 10,000 psi. In this field, top-tier material quality is simply non-negotiable. Section 3. Let's see exactly where this high-performance concrete gets applied across our infrastructure. A really common misconception is that pre-stressing is only for the bridge girders that cars drive on. Not true at all. The PCI manual introduction shows us its uses in the substructure are pretty much limitless. For instance, pre-stressed piles are fantastic because they take the heavy impact of being driven into the ground like champions. We also use precast pier caps, columns, abutments, and even full deck panels. Building things as factory precast pieces gives us strict quality control and makes the entire skeleton of the bridge way more durable. Let's move to Section 4, applications directly in bridge superstructures. Just look at the massive precast elements we're talking about here. On one side, a colossal piece is being lifted. On the other, the final result, an incredibly complex curved viaduct. This is where precast, prestressed concrete truly shines. Geometry. Because we cast these in a controlled plant with adjustable steel forms, we can pull off highly demanding curves and banks. Trying to pour that concrete on site, suspended over heavy traffic or a raging river, that would be an absolute logistical nightmare, trust me. Now, depending on the challenge, we choose different structural systems. The manuals highlight a few industry favorites. We have segmental bridges, which are the kings of long spans. We have continuous spans, which maintenance crews absolutely love because they eliminate those awful expansion joints, meaning a smoother ride and zero water or salt leaking through. We also use multiple beam decks, like box or decent slabs for rapid builds, and spliced eye girders that let us cover enormous distances by connecting shorter beams right on site.
And speaking of connecting beams, check out this precast segmental element. See those holes that look like pipes? Those are post-tensioning ducts. Remember, we have pre-tensioning at the plant and post-tensioning in the field. In these segmental bridges, we bring these short, full-width blocks to the site. Then we thread steel cables through those ducts and hydraulically tension them after the segment is in place. It's a highly cost-effective way to build massive bridges right over cities without needing a forest of scaffolding from the ground up.
Section 5. Let's ground this theory in some real-world case studies.
Our manuals cite some truly historic milestones. Take the 10th Street Viaduct in Lincoln, Nebraska, famous for its innovative use of spliced eye girders to achieve huge spans in a really tight urban area. Then there's the Gallup East interchange on I-40. There, engineers proved they could completely ditch the heavy interior diaphragms, which radically simplified construction. But my absolute favorite is the U.S. length record for a single girder, an incredible 223 feet. The secret? Lightweight concrete. If they had used regular concrete, it would have been way too heavy for trucks to transport down the highway. Just a brilliant solution.
At the end of the day, all this theory translates to real benefits on the job site. Look at that challenging mountainous terrain. By using precast, prestressed concrete, contractors basically assemble these structures like a giant Lego set. What do we gain? We drastically cut down traffic disruptions. We stop worrying about bad weather ruining a traditional concrete pour. And most importantly, we massively improve worker safety. Crews spend way less time suspended over dangerous drops and more time just assembling quality verified parts.
To wrap up this explainer, I want to leave you with a challenge. Today, the introduction of ultra-high performance concrete, or UHPC, is giving us compressive strengths well over 17.4 KSI. That's more than 120 megapascals. It even has the ability to resist tension and avoid microcrocking all on its own. So, knowing everything we just covered about the magic of pre-stressing, I have to ask you, with these incredible new tools, how far will our generation push the absolute limits of bridge engineering? The future of infrastructure is literally in your hands. Thank you so much for joining me today, and keep designing with excellence.